Swayam Prabha. Digital India. Educated India.
Today's topic is regression. What do we mean by regression? See, many a times we need to develop a model equation to predict the values of a dependent variable based on the values of the independent variables. So we want to find out what is the value or what could be the possible value of a dependent variable when the independent variable is known to us. For this, we need to develop some kind of mathematical equations that can only help us to predict. Now, an example of this is let us establishing a relationship between yarn count and strength. So, strength depends upon count of yarn, that is fineness of yarn. Therefore, strength is a dependent variable and the count of yarn is independent variable. Similarly, for a fixed value of yarn count, the strength may vary due to many reasons, such as twist variation, local mass variations, or inadequate mixing of fiber, etc. So these are possible. So other than count, there could be other sources of variations also, which can also play a role. So if we want that strength to be a function of count, twist, local mass variations, mixing quality of fibers, or how homogeneous the mixing has become, then it could be sometimes a multiple regression. But our focus in this particular just now will be on not on multiple regression, but only regressions where there is one independent variable and one dependent variable. What we need to establish a relationship finally. Relationship between the mean of the dependent variable and independent variable. And this relationship is known as regression curve of y on x. So y becomes my dependent variable, which is placed on the y-axis, and x is the independent variable, which is placed on the x-axis. So we say regression curve of y on x. As an example, this is very common example for us, that humidity and moisture content in cotton yarn, or it could be viscose rayon yarn, it could be wool yarn also. We all know that these fibers, cotton fiber or wool fiber or your linen fiber or viscose rayon fiber, all of them, they absorb moisture, and how much moisture they can absorb depends also upon on the humidity. So let us say we have a data on the X humidity and moisture content. So humidity values are given in column 1, that is our X, and moisture contents are given in column 2, which is our Y. Now if this data is with us and if we plot it, we make a scatter plot, then we get the points as you see in this graph. This is what is known as scatter plot. And if we study this scatter plot, what we can observe there are two main points that we can observe. One is the moisture content increases with humidity. As the humidity goes up, increases from 30 to let us say 60, 65, 70, you see moisture content is going to increase. That's a general observation. And it appears from this the pattern that there is a linear relationship between these two variables, humidity and moisture content. So humidity is an independent variable, whereas moisture content is a dependent variable. And the points are the way they are shown here. There is a pattern, and this pattern appears to be that moisture content is going to increase as we increase humidity. Now, if we try to put a trend line you can always plot if we work on Excel sheet, and you will find that, or even if we do not use Excel, from the way the points are distributed on this XY plane, we can draw a line and say that it appears that there is a specific trend, and the trend is linear in nature. So let us say X is the humidity and Y is the moisture content. And a linear relationship between them will mean Y can be described by this functional relationship. Y is alpha plus beta X. X is given here, humidity, which is independent variable, and Y is the dependent variable, that is moisture content. In linear relationship, we are all familiar with the equation of straight line. So this is typically the equation of a straight line. Y equal to alpha pairs beta X. Alpha and beta are the population parameters of the true regression of Y on X. So we have just taken a samples of let us say, if there are, suppose here, how many points are there? So we have, if we count it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 points, 11 data points. That means this is a small sample where n value is just 11. But if we go for the very large population, if we take more and more readings and go for very large number of readings, then the relationship between the moisture content and humidity, that is what is expressed by Y equal to alpha plus beta X. But generally the values of alpha and beta will remain unknown to us because we will not be able to take so many samples. So we need to, whenever we work on sample data, then we say whatever we are trying to find out from sample data, they are all basically estimates. So our job is now to feed a line to the sample data by estimating the value of alpha and beta. We need to estimate what is the actual. We'll never know the actual value of alpha and beta, but we need to get an estimate. Let us say the estimates are A and B. And therefore, we can write the equation as Y equal to A plus BX. So alpha is replaced by A and beta is replaced by B. So A is an estimated value of alpha and B is an estimated value of beta. And that becomes my simple equations. Now if we want to formally state this, you can say that we have n pair of observations, x1, y1, x2, y2, xi, yi, xn, yn. It is reasonable to assume that the regression of y on x is linear. That is, and assumptions. We need to determine the line which provide the best fit. That is what is important for us to know. And the relationship based on the estimated values of alpha and beta is stated by these equations, that is y equal to a plus bx. And here in the diagram what we show here, that some data points are there, and there is a line which is passing through the data points, and it's a straight line. So predicted mean value of y for a value of x, which is xi, will be what? We represent this value of y. This is estimated value, so we will not write y, we write it as y hat. So hat indicates the estimated value, and we use this equation a plus b, and x is replaced by a specific value of x, which is xi. So let us say this is my xi. So at the value of xi, we find out what is the value of y, and that is what is shown here by this black dot. So that is the value of y using this equation. So this is my estimated value of y, and so estimated value of y, I am representing it by y hat. So y hat is here, and actual y, the actual data point is not that. See, all estimated values of y will fall on this straight line, and this straight line is the regression line. So on this line, if I take any other value of x at any point, the data point will appear on the straight line only. However, if you look at the actual data points, they are not, some of them may fall on this line, some of them may not fall. They may be above the line, or they may be below the line. That means there are certain distributions in the data points. So the actual value of y at a given value of xi is here, whereas this is the data point. I am showing it by this red color. So this is the actual, but if I try to find out this value using this equation y equal to a plus bx, I find the data point to be here. That is my estimated value. Now, there is a difference between the estimated value and the actual value. So actual value is here. So this is actual, and that is estimated. So difference between these two is shown by EI. This is the deviations between the actual and the predicted. So actual is yi and predicted is y hat. The difference between these two is shown in this diagram, which we call EI, that is error. And we write what? Yi and y hat equal to a plus bxi. So this is my error. Now, EI equal to yi minus a plus bxi, as we have written in the previous page. Now, since we cannot simultaneously minimize each of the EIs, we try to make their sum as close possible to 0. So we have to have a line placed which is passing through all these points in such a way that the minimum value, the EI value has to be minimized. We try to make the sum of the EIs as close as possible to 0. However, sigma EI can be made equal to 0 by many choices of totally unsuitable lines, for which the positive and negative error will cancel each other and you may get still a 0 value. So there are several lines possible. That means if I can pass several lines through those points, which will give me sigma AI to be 0. So for each xi value, I find out what is the corresponding EI, and if I sum them up, I may get 0 value, and there is a possibility that I can draw more than one lines through those points which are passing through that cluster of points. So what we do, we apply the principle of least square, which says that sigma EI squared needs to be minimized, not EI. But CI values could be positive and also could be negative. Some EI values depending upon whether the point appears above the regression line or it appears below the line. If I add them together, it still may give a value 0. So best possible solution is that we will try to make sigma EI square close to 0. So if it's EI squared, it basically means yi minus a plus bxi whole square and then sigma. So that means all these distances, see if I take another value of xi, the y hat is here and this is the error. For another one, this may be the error. So the error bars are basically the vertical distance between the point and the line that describes the linear relationship between the two variables. So this is basically equivalent to minimizing the sum of squares of vertical distances from the points to the line. We are still not, we don't know which is that line. We have to identify that line. And if we want to identify that line, I need to know what is the correct value of A and what is the correct value of B. The moment A and B are known to us, I can draw the line. Now, the next step is to minimize S, where S indicates sigma EI squared. That is sigma error squared. We have to differentiate the equation 2 with respect to A and also with respect to B. With both, because if you look at this equation has A and B. We need to differentiate with respect to A and equate it to 0 to find out what is the value of A. So first of all, what we do, we take this equation, delta S by delta A, put it to 0. If we differentiate this, we get this. And if I go the next step, cancel the common factor -2, we arrive at these equations. Equation 3. Two will move outside. So, and sigma yi, sigma A means NA, and it will be sigma B sigma xi. This is what will be left. And from there, we can immediately write, if I divide all of them by n, we can write sigma y by n equal to a minus b sigma x by n. And therefore, we can write a is sigma y by n is y bar. And what is my b? This is going to be a plus sign here. It is going to be minus b x bar, because sigma x by n is x bar. Sigma y by n is y bar. So a is y bar minus b x bar. So y bar is the mean values of y and x bar is mean values of x. So you see, this is the equation that we arrive. A is y bar minus b x bar. But unless I know b, I cannot find out a. So we now differentiate with respect to b now. So before that, what we do in the same equation, we replace a by this, because we have found out what is my a. A is y bar minus bx bar. So a is replaced by y bar minus bx bar. And after that, it becomes yi minus y bar minus b common xi minus x bar. Same equation, this is just substituting the value of a, and now we differentiate with respect to b. Now you see, in this equation there is no a left. So with respect to b, if we differentiate it, this is the differentiated equation now. You do the differentiation carefully with a, use your pen or pencil and paper, and you see the differentiations. If I do this, from there we can write again that b is going to be sigma yi minus y bar into xi minus x bar divided by xi minus x bar whole square. It is just a simplification from here. It is after, we can say, simplifying. After simplifying, you'll get this. 2, you have to take it out. Sigma, whatever is left, you carry on. Simplify, and you will get equation 5, where I get only the value of b. So value of b you are getting in terms of x bar y bar and the xi yi data points. And once I know b, I use this b here to find out what is my e. And once a and b are known, the equation of the line will be known. So we are trying to find out the value of a and b by the process known as least square estimate or least square technique, where we are trying to minimize the square of the deviations from the mean, from the line, not mean, from the straight line. That whatever errors are there, square of those errors, sum them up, and we are trying to minimize that function. This line will be the best describing the relationship between x and y. So if all the data points fall on the line, that means all the vertical distances are 0. In that case, there is no error. Now to simplification of the calculations, what we do, we see the two equations for A and B, and we need to know what, for A I need to know what is X bar and Y bar and B. Similarly for B I need to know the multiplication of this and summation. You look at the numerator, and the denominator we have the deviations between Xi and X bar, square them up and then sum them up. This is what we need to know. This is a very tedious calculation, so we need to make the calculation simple by simplifying these expressions. X bar and Y bar are very simple. You sum the X and divide by N, sum Y and divide by N. Now this expression X minus X bar, or you can say Xi minus X bar, same, can be simplified into this: sigma x squared minus sigma x whole squared by N. Similarly, Y minus Y bar whole squared can be simplified as sigma Y squared sigma Y whole squared by N. And summation of these yi minus y bar into xi minus x bar also can be simplified as this, as shown it here. So these are basically we are trying to simplify in order to do the manual calculation easy and faster. And after simplification, what we need to do now to find out the value of A and B, that we only need to know what is the value of sigma x, sigma y, sigma xy, sigma x squared and sigma y squared. There is no need to take the deviations and then square them up and then add them. It's a very lengthy process. Obviously, if you use computer, we can do it very fast. But you need to also know what the computer is doing. So this is what we need to have. X and Y values always available with us. We'll find out what is sigma x, what is sigma y. Then what will we find? We multiply x and y and make another column and find out what is sum of x into y. We'll again multiply x squared and sum them up. We find out y squared in another column and sum them up. Here, that simplified formula that we have written in the previous, here is the proof of that y sigma x minus x bar whole squared is equal to sigma x squared sigma x whole squared by n. These steps are shown here. You can follow these steps and easily you can work out y sigma x minus x bar whole square is equal to sigma x squared minus sigma x whole squared by n. Similarly, y this yi minus y bar into xi minus x bar. If I again go for simplifications to arrive at a very simpler, you can say, formula like this, the steps are shown here. If we go through this, sigma xi minus x bar whole square. So within bracket it is a minus b whole square formula. So that is what you apply. And then you take out the bracket, the first bracket. So it is b sigma x square, it is sigma x bar square, and this is 2x bar into sigma x. So we go for one more step, sigma x square, sigma x bar square. There are n number of data points are there, so it will be n x bar square, and this will be 2x bar and sigma x equal to nx bar. Why? Because x bar equal to always sigma x by n. Therefore, nx bar, if I multiply these two, it will give me sigma x. Hence, I am writing it is n x bar. And now one more step, this does not change. This is 2n x bar square and this is n x bar square. This is minus sign. So we are left with 1 n x bar square. This is thus. So this is sigma x square and minus n x bar square. We write it as sigma x by n whole square. And if we go for further, n and n square will cancel as we will left with 1n, and this is what we will finally arrive. So this is what we will get if we go through these steps one by one. We will be able to find out. So this is basically the proof of whatever we have stated in the previous slide. How did I arrive at these values? Similarly, why this value is equal to this? If this question comes to your mind, then these are the steps you have to follow. Find out why is it like this. Now we go back to the original example of that humidity versus moisture content. So in that example, these two values are given, humidity and moisture content. We need to know, add 3 more columns. One is xy, another one x square, and the third one is y square. So we start with 2 columns. These are the serial numbers. And we add 3 more columns, xy, x square, y square. So we have to first find out what is the value of b, and b simplified formula is this, and what is there in it? Sigma x square. So what is the value of sigma x square? So x square, I sum them up, I get this figure. This is my sigma x square. So whatever is there in this row, they are all summation values, and these two are average values is written. And then sigma x whole square divided by n. So you see, just substitute the values from here, 24529, and this value is 533 sigma x whole square by 12. There are 12 number of data points or paired data. So the figure is 855. We get it. And now we want to find out what is the value of y minus y bars whole square. Also we can find it out because y minus y bar whole square equal to this. And if we follow similarly, just take the values from the table and place it here, you get a figure 74. And now if I want to find out this one also, y minus y bar, x minus x bar multiplication, and then sum them up. The simplified formula is this, sigma xy minus sigma x into sigma y by n. So we have sigma x here, this is my sigma y, this is sigma xy, and n is also known. So just substitute and get the figure which is 230. So now I can find out what is my value of b. So to know the value of b, I had to find out these figures, and we get a value which is 0.269. That is the value of b. And now we need to know what is the value of a. A is y bar minus bx bar. Y bar we have seen in the previous slide, and x bar also is this, and b value is this. So we find out what is the value of a, it is this much. So the equation of the regression line becomes y equal to minus 0.95 plus 0.269x. And if we go by Excel and then just try to find out what is the equation. If you go to where the Excel, go to the trend line, You use a linear relationship and you find out the equation. This is the equation we get. So this equation is as per Excel calculations, and you see they are exactly same. So one is by manual calculation, the other is by straight away from Excel. So Excel give me this result, and manual calculation also gives me same result. Obviously, manual calculation is very time consuming, and you say it may take some at the same time there is a chance of you can commit some errors, some mistakes. Excel will not do that, but we need to know what is working behind the Excel, and therefore this is what I have shown you, so that if it comes on a in case of examination, obviously may not be allowed to use laptop or desktop where Excel is there. You need to know how to do the calculations. And the regression line with the equations is given here. This is the line, so we call it the best fit line. And you see, definitely the line is not passing through all the points. So some points are above, some points are falling, touching the line, or some points are below the line also. So we call it the best fit line. Sometimes when the relationship may not be linear, we can transform the relationship and make it linear, and then use it also. In many engineering problems, at times we need to plot paired data on various transform scales, such as square root or logarithm scale. In order to determine whether the transform data point falls close to a straight line or not. This is what many a times we need to do in many research, even in textile research also. This is what is required sometimes, that we transform the data and then check whether a relationship, a linear relationship exists between the two variables or not. Like wicking height versus time. If we plot age versus t, it is a nonlinear curve. But age versus root t, if we plot, it gives you a straight line curve. So there are many more examples like this. In many situations this may come. So therefore you need to know this also. Example, there could be reciprocal function like this, y equal to 1 by alpha plus beta x. We can easily transform it into linear function by writing 1 upon y equal to alpha plus beta x. So 1 upon y becomes my new y. So it becomes y dash equal to alpha plus beta x. It becomes a linear relation. And then we can apply. We can get an estimate of alpha and beta by considering the point xi and 1 upon yi. That is what is, if we write y dash, that is what is y. Or a power function y equal to alpha x to the power beta. This also we may face many times. This can be also transformed by taking log. If we take log on both sides, log y will be log alpha, beta log x. So this is also can be done, and we get a linear relationship. We will now give you an example of this. The data below pertains to the demand of a product and its price charged in 5 different markets. So price and demand values are given. Yes. And if we only focus on these data and plot them like a scatter plot, we find this is the way the points are located. So points are located. So you see, as the price rise goes up, the demand falls. So this is the definitely a downward fall. And if we try to fit a straight line, then you see this is the trade line that it will appear. But it appears, if I look at the way the points are there on the xy plane, that it appears there is a nonlinear relationship between these two. A nonlinear relationship, maybe it will be able to better describe the price versus demand curve. So if that sort of questions comes to the mind, then what we do, we transform the data into log x and log y. So these are my new transformed data. Then if I take this data and plot, then we see there's a straight line which is touching all the data points, and equation of this line is log y equal to minus 2.3608 log x plus 4.4343. And so this is what we have drawn in this case using Excel. When I do transform data and use it in the Excel, this is the equation I get, and you see the straight line is going to fit it well. If I direct from Excel generated, if I go by power law, then this is the equation that we get. So both of them actually were generated by Excel only, and the relationship that we get using log x values, log values, is this. So I write it here, and if this is what we transform into the original values, we get this equation y equal to 27183 x to the power minus 23608. So this is actually coming from here, and this and these equations are practically same. These equations and these equations are practically same. So even after the transformation actual data to the log values, and then if I plot it, we get again a straight line, and that straight line equation then can be transformed back to the original, to bring it back to the original scale, whatever is the original unit, and you can do that also, or we can also directly use Excel to get these values. So this is what I am trying to say, that for that is sometimes even some nonlinear relationship can be transformed into a linear relationship, and then we can plot the data and see that whether there exists a good linear relationship between the two variables or not. So with this, we close this particular session on regression equations. There are many more, I can say many more things to learn about the regressions. We are not going to take them in this particular, in this, you can say in this course. We're going to not touch them. There are many more things to learn. So we are just discussing the very basics of regressions. What does it mean? How to find out a relationship between the two variables? What is the basics? What is the theory behind it? How do I arrive at these values? Whatever the values of A and B is there. In some textbooks, you may not find the detailed derivations, and therefore some derivations I have given it so that you can learn quickly and you'll be able to grasp the fundamentals of the regressions. Okay, so we close it here and thank you. We'll see you again, and in the next we're going to discuss correlations. Thank you.